Hello and welcome everyone. This is Peter Koluzny. I want to quickly introduce myself because I will be your instructor in this course. I started my career in networking back in 2007, which is when I got my first CCNA. It was CCNA in security. Now, I also got my CCNA in routing and switching. I also took the same approach in 2008 for CCNP, and then eventually in 2009 I was finally able to got my CCIE in security. It was version 4 exam when I took the lab. Now a couple words about my background and experience. I am currently running my own training company, which is known as Navadyne. I am also doing some CCIE Security version 5 technology courses for INE. I used to work as a senior instructor for IP Expert, and obviously I am also working as a network and network security engineer. I've been doing this since 2007. I've been working for many different companies. Now, in case you guys have some questions about the course or about individual technologies, you can always reach me at piotr@andytrainings.com. You can also take a look at my profile on LinkedIn. If you're looking for some news or promotions from Navadyne, it's going to be a good idea to visit us on YouTube. We used to upload full videos and also video samples from time to time. You can also find us on Facebook. Plus, it's going to be obviously also our website where you will be able to find the information about upcoming products. This is also where you will find some of the blog articles. This website is always going to be updated first before any other sites, so it makes perfect sense to visit us over here. Okay, and just to quickly show you this, here at the top you will be always able to find information about the upcoming promotions. And then towards the bottom here, you will be able to find information about individual products that were released and also about the upcoming classes for security and routing and switching. You can also take a look at the blog. There's going to be a lot of useful articles you will be able to find over here. This stuff is going to be updated with a bunch of new articles, so you can also visit this portion of the website. Okay, and finally, I want to say thank you for choosing and supporting Navadyne, for choosing us as your training partner. I hope you guys enjoy the course, and happy studies to all of you. Thank you. We will now talk about ASA fundamentals and basic configuration. Cisco ASA is an example of an advanced next generation firewall, which means that this device is going to offer some sort of sophisticated functionality comparing to regular stateful firewalls. Well, obviously it still provides those stateful filtering capabilities like any other regular stateful firewall does, but those capabilities in case of the ASA are pretty extensive. It allows us to not only inspect communication at layer 3-4, it also allows us to go up to the application layer. It allows us to configure and tune some of the application layer settings or just the behavior of the inspection engines. And in case of certain protocols, the inspection options will be pretty sophisticated. As I said, the main application of an ACL is going to be to control traffic. And this is when you'll apply our access list on one of the interfaces of a router or a switch. Now remember that an access list, once it is applied to an interface, it is going to be controlling communication through the router, but also to the device. As we will see in case of the ASA firewalls, an access list is used to generally control communication through the box. In this session, we will talk a little bit about different terms and concepts related to security. And I would like to start with the different types of data. There are actually two main ways to classify the information at a very high level. We have a data which is sitting in one place, like on a storage media, maybe a laptop, maybe a hard drive. This is what is known as data at rest. and then which is actually as opposed to the data in motion, like when your data is moving throughout the network. Maybe you are sending a file from your network to someone else. So data at rest is information that doesn't move, it just sits in one place, versus data in motion is the information which is being sent, exchanged over a network. Now, as far as those different security terms and concepts go, well, I talked about the types of data in the initially here in the beginning of this session, because there are going to be actually different ways or just methods to secure this data depending on what type of data we are dealing with. So some solutions are going to work for both, for the data at rest and in motion, versus some others will only work for the data at rest. And the first security term I got here is a CIA triad, which is what describes a model used in information security to ensure three critical functions or just elements of a secure environment. We have what is known as confidentiality, integrity, and availability. Now, if you think about confidentiality, it's basically a process of ensuring that certain information is hidden from unintended parties. Like you own the data, but you only want to make this data available to specific recipients, maybe the other organization, maybe someone within your own organization. But you don't want people from the outside to be able to either get this data or basically read it. And now if you think about the different types of data, the data at rest and in motion, now in this first case, there are actually at least two different method solutions you could use to ensure confidentiality of the information. You could take this hard drive where you have those files, where you store the files, and you could put this hard drive into some sort of a cabinet, secure cabinet, lock it, and as long as you're the only guy who owns the key, no one else is going to be able to read this data. This is obviously a simplified explanation, but I think it makes sense. The other solution you could potentially use here would be to encrypt that information on that hard drive. You could actually combine these two solutions, but in case of data in motion, you will probably not be able to do that. Because when we talk about the data which is moving throughout the network, well, even if your own organization is actually secure, it doesn't mean that the network that you will be using as a transport when you send this information from your organization to someone else, it doesn't mean that those networks in the middle are also going to be secured. So someone could potentially see this information, and here locking this data to a cabinet obviously is not going to work. So the way we could implement confidentiality at that point would be to use, for example, encryption. And a similar process is going to apply, similar logic I should say, is going to apply to integrity of the information. Integrity in general refers to keeping the data in its original state, or just ensuring that the data was not modified at any point of its existence. No matter if you're keeping the data on a server, you store the files in a single location, maybe in multiple locations, you want to make sure that this data remains unchanged. The only people who are, or systems which are allowed to modify the data, are those authorized systems or authorized individuals. You don't want anyone from that group to be able to modify this information. And the same logic applies when you send the data over a network. Obviously, what I send to my peer, I want to make sure that my peer gets the same stuff what I sent in the first place. I don't want those other parties to, I don't want my intended destination to get something else than I initially sent. Now, this would mean that my data was modified, and integrity is supposed to ensure that this is not going to happen. Now, technically not that this is not going to happen, but any potential modification of the data is going to be detected. And like in the previous case, if we are talking about the data at rest. What we could do is going to be to lock this information to a cabinet, physically secure the files, and as long as only authorized individuals have access to them, everything should be fine. But as long as the data is moving through the network, well, here the situation is going to be different. We'll probably use something else, which is going to be known as a hashing function to ensure the integrity of the information that we are exchanging through the network. And finally, there's also something which is known as availability. This is what ensures this term describes a process of ensuring that our data information remains available to the end users. And at some sort of a level, there are different, needs of different organizations, the different levels that you want to make the data available on. Like it could be, those 5 nines where you want the data to be available 99.999% of the year, but in some other environments, 95% might be acceptable. So it depends on the specific needs, but obviously the goal in general is to keep that information, make this information available, well, ideally forever. This is not going to be the case, unfortunately, pretty much in any environment. We know that even when you build redundant environments, redundant solution, there is always something that was not predicted that can happen, and is going to eventually lead to losing that availability. Now, a couple other terms related to information security and security in general. We have what is known as principle of least privilege, which generally describes a process of ensuring that our system or individual will perform its functions with a minimum set of privileges. Or in other words, the privileges, the rights a system or individual has allow that individual or that system to function properly, to perform all of its required functions. So in simple words, we can say that you don't really want to allow a given device or a given employee to do something more than that person or system needs to do to perform its work. Like an example I can give you is, well, think about a switch with multiple switch ports. One of those switch ports go to a printer, and we know that the role of a printer is just to print the documents. So the question is, how would you actually implement that principle of least privilege on that given switch and this particular switch port so that the printer can handle its task, can function? Well, obviously the way you would do that would just to allow the printer to connect to a printing server and block all other communication. Because you could potentially open access to everywhere, like allow all communication from that network printer to everywhere, including Telnet, SQL-based communication, SSH, HTTP. But the question is, does the printer actually need those services to function? And the answer is no. The only thing that the printer needs to be able to access is going to be that server, which is somewhere in the middle of our network. So here, a solution would be allow just this single connectivity and then block everything else. Another term related to security we have here is defense in depth, which now describes a process of deploying multiple solutions and multiple mechanisms in our system, in our environment, to secure it. So in other words, we don't really want to rely on a single technology, like a single solution, to protect our system. And this concept goes even one step further. So we will be deploying multiple different types of solutions, different mechanisms, and in addition to that, for individual mechanisms, we will potentially also deploy them at multiple places in our environment. Like think about the firewalls. You'll probably want to have one in the internet edge, but how about if you put another one in the data center? This is obviously not going to hurt. You want to have those firewalls at different places so that when one level, one of those mechanisms is somehow compromised, you still have a backup, you still have some other solutions in that system which could stop the attack from spreading any further. Now, in certain environments, and this is actually a pretty common practice, let's just stick to those firewalls. What people do is that they, in addition to deploying those firewalls in multiple places, like on the edge, on the end host, in the data center, they also rely on multiple vendors when they deploy those solutions. Because there is always a potential that something wrong happened in the code, or just there is a problem, there's a bug in the appliance, hardware appliance itself. And if all your devices come from a single vendor, this single bug can be exploited and leveraged in multiple places. Now, separation of duties, this one applies more to just the individuals. So the separation of duties is supposed to ensure that you have more than one person to perform a given task or a operation. So instead of relying on just one employee to perform a specific function, like for example, administer firewalls, you'll have at least two people so they can act as a backup to each other. Like when one of those guys goes for vacation, maybe got sick, you want to have someone who's going to be able to take over the responsibilities. You want to have that backup. And this is also needed to prevent against theft of the data and against fraud in general. This one applies more specifically to the financial environments. Last but not the least, we have accounting and auditing, which is a process of keeping a record of what is going on in our environment. We want to know exactly what happens, when it happens, and who's making changes if there are some changes being made. So it's like a process of logging of those activities that happen in our network so we can access this information at a later time. And now a couple terms related specifically to the security of information. An asset is going to be anything in our organization that has a value to us. It could be something tangible, like let's say a computer or just any other piece of hardware, or it could be something intangible like intellectual property, like a list of contacts, or just information in general. Then we've got a threat, which is anything that can pose a danger to our assets. And it doesn't necessarily have to be an attacker, like a hacker. It could be a malicious software, like virus, some other sort of malware. It could be an environmental disaster. So there are multiple groups of those threats, and we will actually discuss about some of those groups in this session. We have what is known as a vulnerability, which is a weakness that could be potentially leveraged by an attacker to compromise our asset. Like you have a web server which is running the old code, it wasn't patched, there is a hole in that software, and when this hole is exploited by an attacker, someone can get unauthorized access to the system. We'll actually talk about this in just a second. I will try to visualize those different terms, how they do match to each other. Next thing we have here is a risk. A risk is kind of like a chance or a probability for compromising an asset. Then we have a countermeasure, which is our tool, a solution that we can potentially deploy to minimize or mitigate a risk. And then the procedure that deals with identifying, assessing, prioritizing, and monitoring risks is known as risk management. And the goal of this procedure is going to be to either mitigate the risks or eliminate those, minimize the risks or eliminate those risks completely. In this video, I'd like to talk a little bit about the threats a little bit about the attacker types, and then focus on the actual attack methods that can be potentially used by the attackers to target our systems. Just a quick recap on what a threat actually is. It's essentially anything that can cause a harm or damage to our system or systems, to our assets. And it doesn't necessarily have to be a technical thing. It can be something non-technical, like an environmental disaster. In many cases, it's going to be just one of the attackers, like a human factor. So there's going to be someone who wants to attack our systems because of a certain reason. And those attackers, they will generally use tools, technical tools, because they are capable of doing so. They can also build their own tools to launch an attack against our system. So we will actually focus in this session here specifically on the different types of attacks, attacks performed by attackers, by malicious actors, so by those individuals who for some reason want to attack our system. So what kind of people we might be potentially dealing with here? Well, definitely with hackers. And when I say hacker here in this session and also in the other sessions, I will generally refer to those bad guys, but in fact, in reality, the bad guys are actually known as crackers. So hackers are the good guys who might try to break to the system, but not just to do a harm. They want to learn how a given system works, and so to better secure it. So crackers is the actual term, but for most people in the industry, and again, we also do the same thing here. When I say hacker, I'm actually thinking about the bad guys. We obviously got the criminals. We have terrorists. We have people who are just disgruntled employees. We've got our competitors, and finally, foreign governments. So there are actually multiple different types of, attackers. And the reason for that is that the motivation itself is different. It could be, in many cases, financial, I think, purely financial thing. But in other cases, it could be just political, stuff. In some other cases, it might be just a revenge. So the motivation is different for different individuals, and that's why we have so many types of the attackers. But those attackers, they will generally work in a similar way when they target our system or systems. They will start with what is known as the reconnaissance attack. So reconnaissance attacks, this is a group of attacks which is commonly fired initially. It's like a preliminary phase to the actual attack. And why? Because during this preliminary phase, the attackers will be able to learn about our network. They will be able to discover the devices that we have within a given segment and even tell what kind of services we are running on those devices. So there is a lot of different tools we can use to fire up a reconnaissance attack. In most cases, it's going to be the scanning tools, so we know what kind of devices we have, what type, and also what services are running on those devices. With social engineering, well, this is actually a special type of attack, I would say, because with social engineering, this one doesn't even need any type of technical capabilities, so it can succeed. Social engineering refers to psychological manipulations. It's an act of trying to fool or trick people in order to obtain some confidential information. So you don't really have to be a technical guy, so you can come in to a company dressed like a plumber, and you say, at the reception, you say that you are supposed to fix a plumbing issue just to get physical access to the facility. That would be an example of a social engineering attack. Okay, another group of attacks is known as privilege escalation methods. They rely on a certain level of access to a system to expand that access further. So like you have a junior admin in your network operations center team, and this guy is only supposed to read the configuration of your routers, maybe switches. So you put this guy into privilege level number 1, user exec mode. You gave this user access to show IP interface, maybe show IP route command was also moved down to level 1. And this guy can generally read the configuration and make some sort of basic verification checks. Now, if this guy is smart enough to say, enable on the CLI, and if you didn't take that command off level 1, and this guy is also able to break the password, he could potentially access privilege level 15, and that would be an example of privilege escalation attack. So the logic is like you start with a certain level of privileges, and then you're trying to expand to get some more privileges, which are actually not intended for you. With code execution, it's basically an ability to fire up, execute an arbitrary code on a system. With backdoors, we are talking about a software that is installed on a system that was previously compromised. So it's like when you compromise a device or just a system, you install a backdoor, and the reason why you want to do that is so you can then access this system back in the future in an easy way, like using Telnet or SSH to the device. With covert channels, we're going to be talking about hidden communication channels. Well, in those channels are hidden in a way that they are not known to the network administrators or just to the owners of a given system. Like you could have a firewall in the network which is allowing TCP port 80, for example, and TCP port 80 we know is used for web communication. Someone could potentially use this port as a covert channel to send some information for the firewall. So in many cases, this also means that one of your internal devices was previously compromised, and someone is communicating with this device using such a covert channel. Doesn't have to be web, it could be ICMP with a special payload to signal that internal device that it should do something, but it's generally a legitimate channel that is used for malicious purposes. Okay, what's gonna happen with trust exploitation type of attack? Now, here the logic goes like that. You have some sort of existing policy in place, and this policy allows some systems to communicate in a certain way. And now the trust exploitation attack is, with that type of attack, you will attack one of those systems, and you will then try, assuming that the attack was successful, you will automatically get access to that existing policy that was in place between the attack device and some other system. So let's say that you have let's take a look at a simple example. Let's say that you have a firewall. This is going to be an ASA firewall, which is configured with a DMZ segment. And this is where you host your websites. So we have a web server on the DMZ, and this web server is also allowed to talk to an internal SQL database. So the firewall allows for this communication, like from the web server to the inside SQL device. Now, how about if someone is actually able to compromise that web server? Like there is an attack going on from the outside, and this web server got compromised. So normally it would mean that the attacker would be able to access the DMZ, but it wouldn't be able to go any further. Now, since this web server has a trust relationship built with the SQL database in a way that the ASA firewall allows communication from the web server down to the SQL server device, I was able to compromise my server. I am now able to access the SQL database using that existing relationship, that existing policy configured on the firewall. Okay, there is also what is known as a man-in-the-middle attack, which is a pretty broad, there is actually a large number of attacks that fall under this category. Those man-in-the-middle attacks can be performed at layers 2, 3, 4, even upper layers. but the goal is always going to be the same. It's when someone is placing in line between the two communicating parties, in most cases just to be able to sniff or just read the data. So it is also possible when you get access to those packets, it is also possible to modify, in many cases, those packets. But the goal is just to put yourself in line between the existing communication, kind of like into the middle of the communication, to see what's going on, what do the devices exchange in the communication. Okay, another one we have here, commonly used attack method, is known as a denial of service. And it's actually very similar to a distributed denial of service attack. So these two attacks, they have one thing in common. They have one goal. The goal is going to be to make a given service unavailable. Like when you want to shut a web server so that no one can access a web page. You will fire up a DOS attack or distributed DOS attack. The difference between the two is that with a DOS, the regular denial of service, there's just one attacker which is launching the attack. In a distributed version, you have at least two attackers, at least two stations that attempt to, target a given system to make the services on that system unusable, to stop those services. In most cases, the distributed version of an attack is performed with the aid of so-called botnets, which are networks of compromised hosts or devices known as zombies. So a zombie is a station that was previously compromised by an attacker. When you have a lot of those different zombie machines, they make up what is known as a botnet, and this botnet can be then at some point activated, like when the attacker sends an activation command, maybe using some sort of a covert channel to those zombie stations with an information about the target of the attack. And last but not the least, we've got password guessing and cracking techniques. There are two major attack types here. The first one is known as dictionary attack. The dictionary attack, well, both of these attacks, we've got dictionary attack and a brute force attack. The goal of these two attacks is just to break the password. Whether you're trying to guess it or crack it, like break it, you want to know what the password is so you can get access to the system. That's the goal of these two attacks. Now, the way you will perform this attack is different here, because with dictionary attack, you will rely on some sort of an external source of information to guess or just crack the password. You will have a dictionary file with a certain amount of words, well, typically words that are commonly used for passwords, and you will be trying those words one by one to see if you have a match, and this way, if you know the password. With a brute force attack, what is going to be different? Oh, it's a little bit less sophisticated solution. You will essentially try to guess a password by trying every single combination of a character and characters. Like in a very simple case, you will start with just one character. You will try all combinations, see if you found a match. If you didn't, you will add another character. You will have then two characters you want to combine. You want to check all the combinations of the two. If you didn't find a match, you will add another one, and so on and so forth. So in many cases, when you get up to 4, maybe 5 characters, it's going to be a very long process what it will take for the device to perform an attack, to guess a password using this solution. Now, the good thing, the advantage of a brute force attack is that it always guarantees you a success. It guarantees a success, but the problem here is that it might take almost forever, to find a match, depending on how strong CPU and the hardware that you use to perform this attack. So you will always succeed, but the problem is always with the time. So in many cases, like if you guess a password in 10 years from now, it probably won't really matter. In our next video, I'd like to talk about different firewall technologies. We're going to make a quick overview of the different solutions that we can deploy in the data plane to control communication. First and foremost, let's think about what a firewall is and what a firewall is not. A firewall can be defined as a software or hardware solution which is supposed to control communication in our network. So we're going to put a firewall into the data plane of the network so it sees all the communication and can enforce our policy. Without having a firewall in the network can be thought of as equal from the security standpoint. So assuming that everyone knows how to get to the segments, to the different subnets that we use internally in the network, that device or person will be able to get there because there is no single device that controls communication. When we then place a firewall in the data plane, the device is going to logically break the network down into multiple zones or just segments, where some of those zones will be more trusted than the other ones. And this is how we will be able to enforce our policy. So in most cases, the internal network is going to act as a very trusted segment. Our DMZ is going to be treated as a semi-trusted network. And then obviously the internet, the public networks, and external domains are going to be treated as untrusted. We will now take a look at different firewall technologies and solutions so we know exactly what kind of tools we can use in the network to enforce our policy. And first and foremost, we're going to take a look at a really basic option known as packet filtering, which is the simplest filtering technology out of all solutions available on the market today. Packet filtering relies on basic layer 3 and layer 4 information that is found in the packet headers. So it's going to make a decision whether to allow a packet or block it based on source and destination IP addresses, maybe port numbers in case of TCP UDP protocols. Now the problem with packet filtering is that this solution is completely stateless and hard to manage. And what do I mean by saying stateless? The problem with packet filter is that when you deploy it on the device, like for example when you configure an access list on a router, which is going to make the router with an access list a simple packet filter, this device will be looking at packets independently, separately from each other. So when it gets a packet which is like a new connection, someone is building a connection from the outside to our DMZ, and the device is going to examine the packet, is going to take a look at layer 3-4 information, and if it has a match in that access list, it is going to take an action associated with that match. If it doesn't have it, the packet is going to be blocked based on that implicit deny at the end of that access list. Then when it gets another packet, which is part of an already established connection, it is going to do the same exact thing. It will not be able to tell the difference between new connections and packets that belong to already established flows, like when someone replies back to our internal device. So this is a main problem when our device is not able to tell the difference between individual sessions or packet flows. And then it makes it really hard to configure our access list, our packet filter, because we will never know what kind of traffic might be coming back to our internal devices. We will be able to build exceptions to specify exactly what communication we want to allow to come in, like the new communication, new traffic flows, like when someone wants to access our web page in the DMZ. But when a packet comes back, which is part of a, let's say, telnet session, established, configured, initiated by our internal device, we will not know what port number the packet is going to be using in the destination in case of the reply, and what is going to be the public address of the server which the client is trying to get to. So if we take a look at this on the whiteboard, should make more sense if we take a look at a simple example. It's going to be a really simple network with just one internal device. This is going to be our host. We're going to have a device which is going to act as a packet filter, which is going to be our router. And this device is going to be configured with an access list. So this access list is going to be applied on that, let's say that this is going to be FO1 interface. This is going to be an untrusted port, which is connected to the internet. And on the internet, let's say that we're going to have two devices. One is going to be a web server, which is what our clients will be trying to get to. And we will have one more device, like let's say that this is going to be host 2. This is going to be just a client who will want to get to our, let's say, email server, which is connected to the DMZ segment. So we will have an internal email server. And if someone wants to send an email to us, it will have to connect to this server, which is once again in that DMZ. Okay, so the first thing I want to take a look at now is where the connections that we are interested in terms of filtering, are going to be originating from. So in every single case, you will have to think about what communication you want to actually control with your firewall. What I'm trying to say here is that you will have to know exactly if you want to control communication which is coming from a less trusted network destined to your more trusted segments, or do you want to do the opposite? Like when you want to control communication from your internal devices, when they go out, maybe to the DMZ, in 99% of cases plus, we will be actually looking at this first option. So we will be more concerned with traffic that is coming into our network from less trusted zones. So in our case, the traffic is going to originate on the internet, and it is going to be destined either to the DMZ or to the inside. So our access list, so it can affect those packets, it must be applied in the inbound direction because the packets are coming to the router. So from the router's perspective and FO1 interface's perspective specifically, the traffic is incoming to the port. And this is why we have to apply that access list inbound. Okay, so this access list will now have effect on this communication. But as I said, the main problem with the packet filtering is that the device is not able to tell the difference between new connections, like when someone sends a packet destined to our SNTP server, versus when someone from the inside connects to our web server, and then when web server replies back to the client, this packet must be also evaluated by our access list. So in this first example here, this is not a big deal because we will know exactly what communication we want to allow into the network. But in the second case, which is when the server replies back to the client, it's going to be really hard to figure out what kind of port the server replies back to and what is the actual address of the web server. And this is because when host 1 initiates that web connection, obviously the traffic is going to be sourced from IP address of the host. It is going to be destined to the web server. And then the source port is going to be something random from an ephemeral range, which is something higher than 1023, like for example 1234. The destination port is going to be 80. So this is the original packet which is sent by our host. Okay, but when the server replies back, the packet from the server is going to look like a mirror image of the original packet. So it is going to be sourced from the server. It is going to be destined to the client, or maybe if we use network address translation, it's going to be destined to a public address that we use for translation. In this case, let's simply assume that this host uses a public address. Then the source port is going to be 80, and destination port is going to be 1234. So it's like a mirror image of the original packet. But if you are now to build an entry in the access list, we would have to know exactly where the packet is coming from. So this would be our source. Where it is destined to, well, we could obviously build an entry for the entire subnet, so this is not a big deal. But we also wouldn't know what are the ports that are being used for a connection. And most importantly, we will not know what is going to be the destination port. So it is possible to build such as access list, but it would be very broad and not really secure. And in certain cases, like when you have a lot of devices that communicate with pretty much any single server available on the internet, the only way to allow those return packets would be to build your access list in this way. You would have to say permit IP any, which obviously defeats the purpose of deploying a packet footer in the first place. Okay, so a solution to this problem is going to be to use a different technology, which is known as stateful filtering. With stateful filtering, what is going to change is that a firewall will now maintain information about the connections in a so-called connection or state table. So a connection or stateful table, this is essentially the same thing, and it refers to a memory structure which holds or just maintains information about the flows that our firewall sees in the network. So the primary advantage of the stateful filtering solution is that our device is going to allow return packets to existing connections automatically based on the information found in that table. Or in other words, our stateful firewall will be able to tell the difference between a new connection or just a packet that belongs to an existing session. So this is going to simplify the overall configuration of our firewall because we will not have to worry about returning packets. They will be allowed automatically. So if you go back to our example here, if we are to deploy a stateful firewall on this router, so I'm going to say that we will now change it to a stateful firewall. In most cases, when you configure a stateful firewall, the device is also going to use access lists in addition to that stateful filtering engine. And our access list will be used to control new connections, like to say whether we want to block new connections or deny them, versus the connection table will be used for this second example, for the second type of communication, when legitimate devices reply back to our clients. So the stateful firewall, stateful connection table, I should say itself, is not capable of blocking communication. It is what tells our appliance, our firewall, whether a packet belongs to an existing session or it doesn't. If it doesn't, it's going to be that access list would be used to make a decision whether to allow or block the packet, versus if packet does belong to an existing connection, our access list is going to be bypassed. So for the second example here, if a packet belongs to a session, and the session is going to be obviously populated with information similar to what's inside of packet generated by host 1. Like the device is going to put the source and destination IP addresses, it is going to put port numbers, in certain cases also some other information like TCP flags, so it knows if this is a SYN segment or maybe SYN-ACK or maybe just a data packet. And this information is going to be stored in that connection table. And once again, when packet matches an entry from that table, even that access list could technically say that it blocks this communication, it will be bypassed. But once again, just to clarify this bypass is only going to work for those already established connections and not for new sessions originated from those less trusted segments. The connections originated on the less trusted networks, they will be still subject to the access list. A stateful firewall has one more advantage over packet filters, which is capability of detecting certain attacks, like for example denial of service. Since we will maintain information about the sessions in our connection table, so we will know the exact state of each of those sessions. Like for example, whether a session is fully established or maybe the session is being established. And because of that information, we will be able to tell whether we have a lot of have open sessions or just embryonic sessions, versus maybe the old connections are established. And this information can be generally used to detect basic attacks, like, for example, the denial of service. Okay, in terms of other technologies that we can deploy in our network as firewalls, we have what is known as an application layer gateway, which is what builds on top of a stateful firewall. So an application layer gateway is still a stateful firewall, but with more advanced filtering capabilities. And those devices are also known as proxy servers. They will be inspecting, in most cases, just a single protocol traffic, like, for example, web communication. So they are generally tailored. They are very specific in terms of what they can inspect, what they can control. But the advantage is that the amount of control that you will have is going to be greater than what just a regular stateful firewall can do. So this is known as deep packet inspection, what you can do with those devices, which is going up to the application layer headers, looking at certain values, also going deeper into the payload of the packets. So there's going to be a lot of different options that you will be able to use on an application layer gateway to control a given protocol traffic. Like, for example, in case of web, it could be stuff like configuring your policy based on individual URLs from the package, or maybe performing reputation-based filtering, or maybe using antivirus software to inspect packets looking for malware. So the actual inspection functionality is going to be really broad and sophisticated comparing to just the regular stateful firewalls. And an example of application layer gateway is going to be web security appliance, which is HTTP, a proxy device, or email security appliance, which is going to be a device that we will use to control email communication, specifically SMTP. Then we have what is known as a transparent firewall, which could be pretty much any of these previous technologies, with the exception of an application layer gateway. So it could be either a basic packet filter, or it could be a stateful firewall. But the main characteristic of a transparent firewall is that this device is going to be forwarding communication at layer 2. So in many cases, the inspection capabilities will remain the same as with the previous methods. What is going to change primarily here is that this device will be forwarding packets at layer 2, or just bridging packets, instead of routing them, like in case of a regular firewall. And the primary advantage of a transparent firewall is that you will not have to make any changes to IP addresses of your existing infrastructure. Like when you want to put a firewall into the existing segment, maybe you've got a DMZ with different types of servers, and you realize that you want to control communication between those servers within that DMZ, it would be very easy to add a transparent firewall. You will not have to change addresses anywhere in the network. And then the last solution, the most advanced solution, is known as a next generation firewall, where an example of such a firewall is going to be an ASA along with firepower services. Well, this technology is kind of like a combination of an advanced stateful firewall, which still contains certain application inspection capabilities with some other services, like primarily in case of the ASA, it's going to be intrusion prevention systems, but also with a VPN, a gateway, a functionality, and some other technologies like, for example, advanced malware inspection, or maybe reputation-based filtering. So this device is not only capable of controlling communication, but inspecting the traffic at layers, let's say, from 3 up to 7, but it can also prevent threats with the aid of firepower services and some other advanced technologies. Another topic I'd like to take a look at is access lists. An access list is an example of a simple packet filtering technology that might be deployed on iOS devices. With packet filtering, what we're going to be doing is that we will be looking at layer 3 and layer 4 headers from the package, and we're going to make our filtering decision based on that information, like, for example, source and destination IP addresses, the port numbers. And the main drawback of a packet filter is that this is a stateless technology. The device configured with an access list will not remember any previous packet packets from a session, it will not be even able to distinguish between individual sessions because every single packet is going to be treated or just inspected separately from other packets. So this solution has some serious limitations. Primarily, the device will not be able to distinguish between new packets building new connections versus traffic that is part of an existing session. But it is still a useful solution, and in many cases, we will be combining it with stateful filtering. Okay, but going back to our access lists, as I said, the main application of an ACL is going to be to control traffic. And this is when you'll apply our access list on one of the interfaces of a router or a switch. Now remember that an access list, once it is applied to an interface, it is going to be controlling communication through the router, but also to the device. As we will see in case of the ASA firewalls, an access list is used to generally control communication through the box. In addition to controlling access through or to our devices, there are going to be some other applications of access lists, where the main of those other applications is going to be classification. Like when you want to deploy your QoS policy, you will first have to classify the traffic which you want to act on. Maybe when you want to do redistribution, when you want to control routes, you will have to select those routes with an access list. So many different features though will be also relying on access lists in their operation. So it is definitely good to know how access lists operate and how we configure them. Every single access list consists of so-called access control entries. So these are going to be those building blocks that make up an access list. And those entries generally consist of two major parts. We're going to have that action part, which is to either permit or block a packet. And we're going to have that second part, which is our conditions, or just what packets we want to act on. Now those entries will be processed sequentially, starting with the first entry in an access list, first entry at the top of that access list. And those entries will be processed top down until we have a match. And at the end of the access list, there is also going to be a so-called implicit deny, which I will discuss in just a few seconds. Now, as I said, every single ACE consists of an action and a set of conditions. So an action can be either to permit or deny a packet, where the conditions will generally depend on the underlying protocol that is used to transport a packet. So we will see different conditions for, like when you say IP as the protocol versus, for example, TCP or UDP. But in general, we will be able to match packets based on IP addresses, the port numbers, and some other fields from IP, TCP, UDP, and other protocol headers. Now remember that when an access list finds a match for a packet, the evaluation is going to stop, meaning that all other entries will not be processed. And as I said previously, at the end of an access list, by default, there is going to be that invisible entry, which is configured as deny any, which means that this implicit entry will block all other packets, meaning packets not matched by our previous custom entries. It is possible to override this entry, like you could end an access list with permit IP any. So then this permit entry is going to act as a catch-all for all previously unclassified packets, or just unmatched packets, I should say. But by default, this deny any is there, even if you cannot see it. Okay, we have two main types of access lists on iOS devices that we can use: standard and extended. Now, as I said, it is generally possible to match IP packets based on different fields. But in case of a standard access list, there is going to be a huge limitation of that type, which is going to be to only look at source IP addresses. So this limitation makes a standard access list pretty much useless for a traffic filtering. The main application of a standard access list is going to be to control routes, like what you send to your neighbors, or maybe when you do redistribution, what prefixes do you want to inject into your underlying IGP or any other protocol you might want to run. The second main application for standard access lists is going to be to control access to your VTY lines, like when you telnet or SSH to the router. Those access lists will be generally configured with a number. It is also possible to build so-called named standard access list, which is just give it a name instead of a number. And the reason I put a star here and also for extended access lists is that those default ranges, they can be expanded, meaning that there is actually another range for standard access lists, and there is also another range than this 199 for extended access lists that you can use to build an access list. Now, same as with standard access lists, we can also build named ACLs and named extended access lists, but the main benefit or just advantage of an extended access list over a standard one is that it supports matching based on not only source IP addresses, but also based on other information that we can find in layer 3 and layer 4 headers, like for example, destination IP addresses or port numbers. So whenever you think about applying an access list to an interface to control communication, you will be applying an extended access list. So first thing, you will have to build an access list, then you will have to apply it. And remember that when you apply an ACL, there is going to be that golden rule that says how many access lists of different types you can have on a single interface. And specifically for IP, you can have just one access list applied on an interface per direction. So whenever you apply an access list, you will have to tell the router if an access list is for the inbound or outbound direction. Now, what's the difference between the two? When you apply an access list in the inbound direction, it means that it is going to affect packets that are incoming to the interface where you applied it. Versus when you apply an access list in the outbound direction, it is going to affect packets going out or just leaving that interface. So one access list per interface per direction per protocol. It is also possible to build access lists of different type than IP, like for example MAC access lists or MPLS access lists, but this is definitely beyond the scope of this session. Okay, whenever you apply an access list in the outbound direction, so once again, when communication affected by that access list is going to be traffic that leaves the port, remember that this ACL is not going to affect packets generated by the router itself. Packets originated by the router are not affected by outbound access lists, and of course by inbound access lists as well. And now a couple words about the differences between iOS and the ASA for access lists. So first and foremost, remember that when you configure an access list on iOS, it takes so-called wildcard masks as the input when you define like subnets or networks, versus on the ASA, it is going to take regular network masks. So for example, when you build an access list on iOS and you say that you want to match packets coming from a single subnet, which is going to be a /24 subnet, you're going to build an access list with a mask of 0.0.0.255. Versus if this was ASA, you will configure a mask like in every other case with a regular or just natural masks. So you will use that 255.255.255.0 syntax. A wildcard mask is like a reverse regular network mask. And another difference is that when you apply an access list in the inbound direction, this access list on the ASA is only going to control packets going through the firewall. Versus when you apply it on the iOS, like on Giga1, Giga2, or any other interface, this access list is going to affect packets traversing the router, but also packets destined to the router itself. That's the main difference between iOS and the ASA in terms of processing of access lists. Now on the ASA, it is also possible to build an access list that is going to control communication to the firewall itself, but we will not be talking about that in this session. This is just a general overview of access lists. Now a couple words about IP version 6 and ACLs. So first and foremost, there is going to be that extended access list, what we can build it is not possible to configure a standard access list for IPv6. And those access lists will generally work like IP version 4 counterpart, which means that entries will be processed sequentially top-down until a match is found. This access list also ends with an implicit deny, and a single access list entry consists of an action and conditions. Well, obviously, for IP version 6, the fields that we will be able to match as our conditions will be partially different. I mean, many fields will be the same, like for example, source destination IP addresses, but some other fields, well, could be included, like for example, extension headers. So generally speaking, fields specific to IP version 6, you will be able to match them inside of an IP version 6 access list. And there is also a very important thing you should think about when you build a version 6 access list, which is that implicit deny at the end of it. In case of version 6 of IP, will block everything with the exception of neighbor discovery packets. Neighbor discovery packets in IP version 6 are used for, among other things, address resolution. So if you were to block those packets, you would also break your control plane. So this is what implicit deny does. It is going to make an exception for those neighbor discovery packets, but if you were to build an explicit deny is going to block all packets, including neighbor discovery. So this is definitely a key takeaway from the version 6 access list session. Okay, let's now take a look at a configuration for both access lists, IP version 4 and IP version 6. In case of IPv4 and iOS, we will be defining the move an access list statement, like when you want to build a numbered access list, or if you want to build a named access list, you will say IP access list, and then give it a name, or just give it a number, like if you were to add an existing numbered ACL, for example. On the ASA, it's going to be a single command where we will use the access list statement, and the way that we will apply those access lists, on iOS we will have to say IP access group on the interface, versus on the ASA we will say access group globally. IP version 6 configuration, the syntax is going to be quite similar here. We will say IPv6 access list, give it a name. Remember that no standard access lists are supported for version 6. And we will apply it with the IP version 6 traffic footer command on iOS. And then on the ASA, the command is the same. It's going to be the access group statement. Right, so let's now go ahead and take a look at an example of how to use access lists. And I want to show you how to build a simple ACL. The first thing for IP version 4 packets, and then also for version 6. What we will do for version 4 is that we will say that router 1 is going to act as my firewall. And we're going to apply our access list on the GigaO2 interface. And we will say that router 3 is going to be the untrusted network, versus my VLAN 112, these are going to be the trusted zones. So we will apply this access list on GigaO2, and we will do this in the inbound direction, because I want to control communication or just traffic originated on that untrusted zone. So first thing, let's think about what do we want to allow a drop. So we will say that packets destined to the switch for telnet and also for web. This is what we want to allow for router 3. And then we will say that we also want to allow ICMP packets to router 2. And then everything else we will block. Maybe let's also make one additional change here. Let's say that telnet packets to router 2, we want to drop those packets and log. And then we will leave this access list configured with an implicit deny initially, and see what kind of changes we will have to make to make sure that our environment is still functional. Because there is going to be a problem when we configure this access list, apply it on the interface, and leave that implicit deny at the end of it. Okay, so let's go to the global configuration mode. Maybe first thing, let's take a look at a quick overview of access lists. When I say access list globally, I am able to select a number, which is gonna eventually affect the type of the access list I am building. Like when I say select something from 1 to 99 range, it means that they want to use those standard access lists. When I say, let's say 101, this means that they want to build an extended access list. And note that there is also that other range, expanded range, for both standard access lists and then another expanded range for extended access lists. If I were to choose something from the 700 to 799 range, it would mean that I want to build a MAC access list. So this is a very basic syntax of that access list command. If I want to build a named access list, I have to say IP access list and then extended or standard. There are also a few other options that you could potentially want to use, like when you want to control how often a log message is going to be generated when a packet matches an access list entry with the log option added, or maybe how many packets you want to generate a log message for. It is also possible to resequence an access list, like change the sequence number of ACEs, and we will be actually looking at this option. So first thing, let's say that we want to build an extended access list. I'm going to call it OutIn, like if this access list is supposed to control communication from the outside to the inside networks. So we can select a sequence number, and then we can either say permit or deny. There's also a few other options here, like dynamic or evaluate, but they don't deal with just the regular traffic filtering. Dynamic access list is more of like an authentication, identity management solution. So we will not be looking at this feature here in this session. And we'll just say permit, and let's select IP as the protocol. Then I'm gonna say any. So this is my source, this is my destination, and we will take a look at the different options we can configure here. So those different options here, they will generally depend on the protocol that we have configured in our access list entry, which is an IP here. The DSCP, this is something that you might want to match when you're looking at the type of service field, the same as IP precedence over here. Then we can also match fragmented packets with this option. We can log packets or log and include the input interface where the packet was received on. We can also use the reflect option when we want to build a so-called reflexive access list, which is an access list that is supposed to dynamically allow packets returning to the client, or just packets which are part of an established session. And we can also deploy access lists that will be active in a given time frame. Like we could build an access list that allows to browse the internet outside business hours, but within business hours it is going to block the activity. If we were to change the underlying protocol, like for example, instead of saying permit IP, we would say permit TCP and then any, we see that those options are generally different. We have some more options here, like for example, greater than, lower than. So this is just to select what ports you want to match, like greater than the number you put here, or maybe lower than the number that you put to the access list entry. So if I say lower than 80, it means that they want to match packets with port 79 down to 1. When I say greater than 80, it means that they want to match packets with port number 81 or above. You can also match individual flags like push or SYN. And obviously those other options that we saw for IP, they also exist. There is also a very nice option which is specific to TCP, a match all and match any, which allows you to match packets, TCP segments, with a given specific combination of flags. Like if I were to say match all, and let's say plus ACK and plus SYN, it means that they want to match TCP segments with a SYN and acknowledgement flag set. Okay, in case of UDP, there is not going to be too many differences from IP. And pretty much the only difference is that you will be able to match the port numbers. The NEQ means that you want to match ports different than the number that you specify in that entry. It is also possible to select ranges of ports. So those options are generally available for TCP and UDP. Okay, so if we are now to go back to our example, once again, the goal of my configuration here is going to be to allow web packets and telnet packets to the switch. Is going to be to drop telnet packets to router 2, but allow ICMP. The telnet packets that will be dropped, you also want to log them. And then we will leave that implicit deny at the end of an access list and see what is going to happen. So it's going to be a pretty simple configuration. I'm going to say permit TCP any host 10.1.1.99 equal to 23. So this is my telnet to the switch. This is my web communication to the switch. Then we will say that we want to block telnet packets, deny TCP any host 192.168.12.2 telnet, and I want to log those packets. We will say permit ICMP to the router, like that, and we will now apply this access list to the interface using IP access group command in the inbound direction. So let's take a look at this access list once again. Again, I want to allow communication to the switch, telnet and web. Then we want to block telnet to the router and we want to log it. And then we want to permit ICMP to the router as well. So if we were to test this from free, we should be able to telnet to the switch, which we do. We should be able to connect to the web port, which we are. And then we should be able to ping our router, which we can ping it. But if I were to telnet to the router, we see that this is blocked. And we should also see a log message is generated on our firewall that says the TCP packet destined to port 23 on router 2 is now being blocked. But one thing that we will not see in the access list when I take a look at the counters here, we see that this implicit deny at the end is not showing up because, again, it is just a hidden command. But what we see instead is another log message that was generated that tells me that my OSPF adjacency is down. And this is specifically an adjacency built between 3 and 1. This one here. So what's the problem? Remember that the access list applied on an iOS device, it not only affects communication through the box, like from 3 to the switch, but it also affects communication to the router itself, which is going to be my OSPF. So this implicit deny is now blocking OSPF packets. It is killing my control plane, and this way also killing my data plane. So free should now lose routes. It shouldn't be able to get to the switch again. If I were to telnet to the switch, I am not able to do it because free doesn't have a route, doesn't know how to get to the switch in the first place. We just created a black hole in our network. So we will now quickly fix it. We will go back to this access list and we will modify its content. And we will add an exception at the beginning of this access list where I will permit OSPF packets. And with this in place, we should see that the adjacency is gonna come up in just a second, which it did. And we should have connectivity when OSPF finally converges. Let's just give it a few seconds. We should see that we will be able to connect to the switch, which we are. Okay, one more thing I want to show you for those version 4 access lists is how to resequence them. Obviously, you could end up in a situation that you would have to modify this access list multiple times, and you might run out of sequence numbers. Like if I had 4 more permits before 10, and I wanted to put another one, I wouldn't be able to do that because I just ran out of the available numbers. So with this, there's going to be a pretty easy to fix this kind of problem with the resequence option of an access list. If I were to say IP access list resequence, and then specify the ACL number, or just name, in my case it is called OutIn, I will be able to specify a new starting sequence number, like for example 10, and then I will be able to give it a increment number, which is going to be how many entries I want to leave between my sequences, so I can use them in the future. Like let's say that we will increment numbers by 20. And when I say show access list once again, we see that we now start with 10. This is our OSPF entry. And then we finish with 90, which is that permit ICMP. Okay, one more thing I want to show you here in this session, as I said at the beginning, is going to be IP version 6 configuration. So we will quickly configure router 1 and 3 with IPv6 addresses. I'm going to configure a 2001:13/64 subnet between router 1 and 3. Router 1 is going to use 1, 3 is going to use 3 in the last tuple, and then we will test IP version 6 access lists. So when we go to router 1, I'm going to say IPv6 address 2001:13:1/64, and then we will do a similar thing of 3 on interface 2. IPv6 address is going to be 2001:13:3/64. I don't even have to enable IPv6 routing on those devices because we will just treat them as end hosts. We will be communicating directly at layer 2 in the single layer 2 network. We just use IP version 6 for transport, so those devices will not be routing those packets between the different layer 2 networks. We should be able to communicate without enabling routing version 6 packets on those routers. So let's say that I want a telnet from 3 to 1, but this time we're going to use IP version 6 for transport. 2001:13:1, and we have connectivity. Okay, so let's quickly build an access list that is going to affect version 6 communication. I'm going to call it OutIn, like in the previous example. Actually, it doesn't allow me to do that. So we will say OutIn6. And then we will permit telnet, all telnet packets. And same as in the previous example, we will leave that implicit deny at the end. So let's see what happens. I'm just going to apply this access list. So once again, the syntax here is going to be slightly different from IP version 4. It's not IPv6 access verb. It is going to be IPv6 traffic dash footer command, how we apply it, and then inbound. So we will now telnet once again. We have connectivity. We see that the counters increase in our version 6 access list. If I were to ping this router, we should see that communication is going to be blocked because of that implicit deny at the end of that access list. Now, how about if you were to change this implicit deny to an implicit one, like for the purposes of logging drop packets? We can easily do this. We can go back to this access list. And we can say that, for example, entry number 50, we want to deny all packets. And just a quick glance at the different options that we have available for matching in IPv6 access list. So generally speaking, it's going to be a similar stuff to version 4, obviously with the exception of fields that are available in version 6 but are not available in version 4. So fragments is available for both, but for example, same as log and log input. But stuff like mobility type, routing type, this is what is known as the extension headers, which is part of version 6, but not version 4. So obviously we will not see those options in version 4 access list, but we will see them here for version 6. The same thing with flow label and authentication. Flow label is not an extension header, but this is also a version 6 specific field. There is also the undetermined transport option, which is used to block packets with not known or missing upper layer header information. So specifically, this is talking about layer 4 header, like when you have something else than TCP, UDP, or ICMP. Okay, but let's just build this explicit deny, and let's say that we want to log drop packets. Show access list. Okay, so as of right now, we don't have any entries here. Okay, if we go back to router 3 and let's say telnet, initially it looks that everything is working fine. I am able to telnet. I am not able to ping like in the previous case. But one thing that is gonna change is that if I were now to clear my version 6 neighbor discovery cache, which is an equivalent of IP version 4 ARP, I'm gonna say clear IPv6 neighbors. If I were now to telnet once again, we see that we don't have connectivity. So the problem we're running into now is that router 3 no longer knows what is the underlying layer 2 address, which corresponds to 2001.13::1. So it is generating a neighbor solicitation packet, which is ICMP version 6 packet type 135. And this packet is now explicitly dropped by my access list. So the key takeaway from this example is that your explicit version 6 deny any does affect neighbor discovery packets. It is blocking them. Versus implicit, which was the previous access list, it does not. We will now talk about ASA fundamentals and basic configuration. Cisco ASA is an example of an advanced next generation firewall, which means that this device is going to offer some sort of sophisticated functionality comparing to regular stateful firewalls. Well, obviously it still provides those stateful filtering capabilities like any other regular stateful firewall does, but those capabilities in case of the ASA are pretty extensive. It allows us to not only inspect communication at layer 3-4, it also allows us to go up to the application layer. It allows us to configure and tune some of the application layer settings or just the behavior of the inspection engines. And in case of certain protocols, the inspection options will be pretty sophisticated. The device is also going to act, or just can act, as a VPN termination point. So we can configure our firewall as a site-to-site gateway or as a remote access gateway to our internal networks. And it supports pretty much every single commonly used secure VPN mechanism like IKE version 1 and 2 for IPsec and also SSL. This device is also acting as a next generation intrusion prevention system when we couple it with the Firepower inspection module. It also offers advanced functionality like, for example, reputation-based URL filtering and advanced malware protection. It is also possible to virtualize a single physical unit into multiple logical firewalls, like when you want to use many different firewalls at different places of your network without having to buy separate physical devices. So we could use this feature to, let's say, sell firewall services to your customers, or for example, to configure different firewalls, deploy different firewalls for different departments. The ASA is also supporting highly available networks. We can deploy ASA firewalls in a redundant fashion, and this can be accomplished by using either failover or clustering solutions. There are two major ways how we can deploy our ASA. We can either go for a physical appliance. Specifically, this is going to be the 5500X series of ASA firewalls. And here, the higher the number is, generally the more performance it offers. So we're going to be talking about things like the overall bandwidth available on the interfaces, like the bandwidth for the firewall. And we will be talking about the inspection capabilities, like how many connections per second can be inspected. The platform is also going to affect things like a VPN peer number and some other settings. And then the second way to deploy the ASA is going to be to use a virtual image, which is going to be installed on a VMware server. There are going to be 3 images to choose from, 5, 10, and 30. And the only difference between those images is going to be the throughput supported by one or another image. The main drawback of a virtual ASA is that it does not support virtualization, or just multiple contexts, and clustering, but it is still commonly deployed in the data centers. One of the first things that we will have to do when we deploy a new ASA into the network is going to be to configure its interfaces. And first and foremost, we will have to select the actual type of interface we want to use, or just interface mode. There are going to be 3 different options here that we can choose from. First and foremost, the simplest solution is going to be to configure a physical interface of the ASA. Just take a single physical port, like Giga1, and configure it. Then the other option is going to be to combine 2 physical interfaces, make them redundant, and then one of those ports is going to be acting as a standby. The other one is going to be the active port. So just one of these 2 interfaces is going to be physically forwarding the traffic, and the other one is waiting for the active interface to go down. So this is how you can build redundancy at that interface level. It is also possible to combine 2 or more interfaces and make them all active, like when you bundle those interfaces into a single logical port, known as a port channel. So the feature is called Ether channel, but the logical interface is called port channel, and this logical port channel interface is going to represent the underlying physical ports to the layer 3 or layer 2 processors. So in this case, multiple interfaces will be active in the same time, and it will be possible to distribute the packets across multiple bundled interfaces. So we will not only provide redundancy, but also increase available bandwidth. And it is also possible to build logical interfaces, which is implemented in the exact same way as on iOS devices. So we can build a sub-interface of a physical port, and the device will separate the packets between those logical interfaces by using layer 2 trunking. And it must be 802.1q what you'll configure on the switch if you want to use that feature. So the ASA is going to connect the switch as a trunk, and you will have to select 802.1q on the switch because this is the only trunking protocol supported by the ASA. Once the trunk is up, you will be able to configure logical interfaces on the ASA by using the interface command when you specify the name of the physical port, followed by a dot and a number. Okay, once we selected the interfaces for our deployment, we will then have to logically configure them with certain settings. So first and foremost, we will have to configure our interface with an IP address. It could be version 4 or version 6 address. It could be both. Remember that when you configure a version 6 address on the ASA, it automatically enables version 6 routing. So it's not like on iOS where you have to say IPv6 unicast routing. This command is not needed on the ASA, so it starts forwarding version 6 package. Okay, then probably the most important setting for the interfaces is going to be to configure a so-called security level, which is just a number between 0 and 100 that describes how trusted or untrusted a given interface is. And this number is going to have a serious implication on how the ASA is going to by default filter the traffic, because as we will see, the traffic that is generally coming from a more trusted interface is going to be allowed, versus traffic which is coming from a less trusted network will be blocked. Okay, then we will have to configure an alias for our interface, which is needed to kind of like activate the interface for traffic forwarding. So we will have to give it a logical name, which is like a description of a security zone that we configured with our security level. It could be something like inside, outside, DMZ. Whenever you call it inside, the device is also going to assume a security level of 100. Whenever you use a different name, it is going to assume a security level of 0. Okay, next optional element is going to be to configure a VLAN number or just a VLAN tag if you want to use or just build a sub-interface. So this is optional. And remember that ASA does not support DTP, or just dynamic trunking protocol, so you will have to configure a static trunk on the switch to the ASA with 802.1q encapsulation enabled. And also, if you plan to use main or just the physical interface for a traffic forwarding, you will have to configure just a native VLAN on the trunk. And the last step is going to be to physically bring the interface up with the no shut command. Okay, so as I said, the ASA is going to, by default, once we enable the interfaces, and this way initialize the firewall, is going to come up with some sort of a logical default filtering policy, which is going to generally rely on the security levels configured on our ports. And as a general rule, the ASA is going to, by default, allow communication originated on a more trusted interface, which is going to be an interface configured with a higher security level when a packet is destined to a lower security level interface. And for the opposite direction, so when a packet originates on a lower security level interface, it is destined to a higher security level interface, the ASA will drop the packet. And it is possible to make exceptions to this second rule by configuring and applying an access list. Okay, so let's say that we have a firewall. Like in a common design, we're going to be using 3 different interfaces, one connected to a single zone. Like let's say that this is going to be our inside, this is going to be the outside, and we will also have one more, which is going to be our DMZ. So in many common deployments, what you will do here, when you will then configure those interfaces, is that you will then assign them the following security level numbers. You will go for something high for your inside, like for example 100, which is the highest number. You will go for something semi-trusted, like 50 for the DMZ, and then outside is going to be typically configured with a level of 0. So this configuration, once the interfaces are up, it also automatically enforces a policy on the packets traversing through the firewall, which is going to be to allow communication from a higher to lower security level interface and block communication going in the opposite direction. So this means that when the packet is originated on the inside, it is able to go out through any other interface, because in our case, all other interfaces are configured with a lower number. So since 100 is the highest number here, it is greater than 50, and it is also greater than 0, the packet is allowed in any direction, from the inside to the outside, from the inside to the DMZ. Now, from the DMZ's perspective, it means that the packet is going to be allowed to the outside, but not to the inside. this one is going to be blocked. And the reason for it is that 50 is less than 100. So obviously this also means that packets originating on the outside, no matter if they are destined to the inside or DMZ, they will be blocked because 0 is the lowest number here. Okay, it is also possible to configure two interfaces with the same number, with the same security level, and by default, the communication between those interfaces is gonna be blocked. If you want to change this behavior, you'll have to use the same security traffic permit inter-interface command. And then a somewhat similar situation is when you want to route a packet back via the same port where the packet was received on. So for example, when a packet is coming on the outside and the device is trying to route it back via outside, this is going to be by default disabled. If you want to enable it, you will have to use same security traffic permit intra-interface option. And when you enable it, this is going to be known as hairpinning or U-turn. This feature is going to be useful in certain VPN scenarios. Like for example, when we have a remote access tunnel. So when someone is connecting to our network using, let's say, SSL or maybe IPsec VPN, we have the ASA firewall, which is connected to the internal network. Then we have the public network. And finally, a client which is connecting, which is building the VPN tunnel. So the tunnel is built from the PC to the outside of the ASA. This is our VPN. So this feature is going to be useful when split tunneling for the VPN is disabled, which means that all packets generated by the PC are destined to the tunnel endpoint, to the ASA. All communication. No matter if the PC is trying to reach some internal destinations, but also if PC is trying to get to public devices, like for example to a web server connected to the internet. So even though the packet is destined to that internet device, it is still tunneled with split tunneling being off, which would mean that unless you have some other exit point here to the internet in this internal network, the ASA would have to route the packet back for the same interface where it received it on. So the ASA got the packet on the outside, and so the client can connect to the public server. The ASA must send the packet back via outside, and then when it gets the reply, it is going to tunnel the reply back to the client through the VPN tunnel. So this would be an example where you would have to enable U-turn or just hairpinning on the outside port so that the ASA can route packets back. Okay, one more thing we will also discuss in this session. It's going to be just a quick overview of how the ASA is routing packets. So the process is going to be very similar to what an iOS device does, which means that our firewall is going to be generally using a routing table to select the egress interface for a packet. So it's still based on the longest match, what the device is trying to find in the routing table. And this match is then selected to find the egress interface for a packet. Like if the interface is directly connected, or if the route points to a next hop, the ASA is going to do the route recursion to find the egress interface. Finally, when we have that interface, we will switch the packet to the egress port, we will re-encapsulate it, and serialize the packet onto the link. But there is going to be one difference from iOS devices, specifically when a packet is going to match an existing translation. Like for example, we translated an internal device 10.1.1.1 to a public address 1234, and a packet is destined to 1234. This would mean that our packet would match a translation entry, and this entry would be used to find egress interface for that packet, and not the routing table. So this is the default behavior of the ASA, unless your translation was configured with the route lookup option. But other than that, the routing process is going to be the same as on iOS. So the device is going to be using routing table to find the longest match. Then it is going to use the next hop or just the egress interface to switch the packet, and finally re-encapsulate the packet and serialize the packet onto the link. And just a summary of the routing configuration for most commonly deployed routing protocols. Just a really basic config to show you the very basic syntax. So in case of static routes, we're going to be using the route or IPv6 route command to configure a static path. If you want to build a default route, you will be using 00 to specify a 0.0.0 prefix with the same subnet. And the main difference from iOS is that you will have to select or just specify an interface which is going to be associated with a given route. Okay, in case of OSPF for IP version 4, we're going to say router OSPF, then specify the process number, and use the network command to enable OSPF on certain interfaces, and also to advertise networks configured on those interfaces. Same exact configuration as on iOS. And then for OSPF version 3, like on iOS, you'll first thing have to build a process globally. So IPv6 router OSPF process number, and then enable this process on individual interfaces with the IPv6 OSPF command. And then for EIGRP, like on iOS, define the AS and enable your interfaces and advertise the subnets configured on those interfaces with the network command. In this video, we're going to talk about virtual private networks and IPsec. A VPN or virtual private network can be thought of as a logical connection, sometimes called a tunnel, that is built to communicate two or more devices that normally don't have IP reachability to each other. Like for example, when you're a large company, you have multiple offices across the world, and for some reasons you want to communicate two of those offices together, you will normally obviously have different choices as far as the technologies goes, which you could use to establish that communication, but the VPN would be one of those options. You could build a VPN tunnel over a public network over the internet, connect those two offices together, and this way the devices connected to one of those offices would be able to communicate with the devices connected to the second office. There are two types of VPNs, two major types of VPNs. We have what is known as remote access and site-to-site tunnels. With remote access, there is going to be a single device what will be connecting to our, well, typically internal network to access some specific services within this network. And this connection will be established directly from the endpoint itself. So the endpoint must be configured with an IPsec software. It must have that IPsec software installed so it can get connected and access the internal network. With site-to-site tunnels, the logic is going to be quite different. The actual endpoints will not necessarily have to use IPsec. It will be other devices what we will use to build the tunnel, known as IPsec gateways. And the second method, also known as LAN-to-LAN tunnels, is typically used to build connection which will connect two or more sites or just networks together. So the devices connected to those networks can communicate with each other over the tunnel. Now, VPNs can be built at different OSI layers. It doesn't necessarily have to be layer 3, like as we will see, what could be done with IPsec. It could be other layers, like for example, at layer 2, you could build a L2TP secure connection. At layer 3, you could build an MPLS VPN, like over your provider's network. It could be something between the transport layer and the application layer, like for example, SSL, which generally resides at layers 5 and 6 of the OSI model, but not all of these methods will actually provide secure services or just secure communication. So you can build a tunnel, you can connect two different sites, for example, but this communication will not necessarily have to be secure. And because of that, the most common choice for building VPNs, especially at layer 3, is going to be IPsec because of the fact that it offers 4 critical security services. We have authentication, which is the ability to make sure that the tunnel that we build is built with the desired communication partner. We have data confidentiality, which is achieved through encryption. So this is how we can hide information from untrusted parties. We have those data integrity services, which is how we will ensure that the data arrives to the intended destination unmodified. And we have a replay protection, which is used to detect old packets coming from old sessions, like when those packets were recorded and re-injected into the current communication stream. Right, IPsec is not a single protocol. It is technically a collection of different protocols, technologies, and standards. And two most important standards that IPsec is built of are known as ISACAMP and IKE. ISACAMP stands for Internet Security Association and Key Management Protocol and is acting as a framework in IPsec that is used to describe the different functions and responsibilities of IPsec for establishing secure communication channels. So specifically, this is going to be key exchange and authentication, and then a set of procedures that describe how we will build so-called security associations, how we will maintain those security associations, and then finally how we will delete the tunnel information. IKE, which stands for Internet Key Exchange, is going to be an implementation of ISACAMP. So this means that it specifies exactly how authentication, key exchange, negotiation is performed, how the actual maintenance, creation of essays, and deletion of essays is performed. And we have two versions of IKE. IKE V1, this is the old standard. The newest version is known as version 2. In this session, we're going to focus on IKE V1. We will have a separate recording for IKE version 2 and just IKE version 2. Another thing that IPsec heavily relies on is going to be cryptography. And I am talking about both versions of cryptography in general, which is going to be asymmetric key cryptography and then symmetric key cryptography. So it's going to be definitely stuff like encryption, integrity checks, and then private public keys or similar functions that also use the asymmetric key cryptography framework. IPsec is going to be using those technologies pretty extensively. And if we were to take a look at the other components of the IPsec framework, we could actually break them down into the control plane and then the data plane elements. So in the control plane, we're going to be dealing with key management technologies, which is going to be known as Diffie-Hellman protocol. So Diffie-Hellman is one of the asymmetric key cryptography functions that is used to negotiate secure keys over an insecure medium. So we are going to be using either the plain old Diffie-Hellman or a newer version of Diffie-Hellman, one of the elliptic curve functions. More on this later. We're going to be looking at authentication here in the control plane, which can be done with the keys, pre-stored keys, certificates, and for those certificates we can use either the original RSA specification or the newer variation elliptic curve DSA function. And then in the data plane, we will be dealing with the security protocols, which is what provides the actual protection for the data packets. We will look at encryption from DES up to SEAL, including TripleDES and AES. And we will obviously look at the data integrity and origin authentication functions, our HMAC variations of MD5, SAJ, and next generation SAJ functions. Now, obviously, since those individual components make up the general framework, it is going to be possible to replace those individual building blocks when they become obsolete. without having to modify the actual framework, obviously. And an example of this is a replacement of Ike v1 with Ike v2, which was pretty easy for the developers based on the fact that Ike is just one of the components of that whole framework. So it was pretty easy to change or just add Ike v2 to the framework without having to modify the entire framework or its other elements. Okay, now let's go ahead and take a look at the actual details of what is going to happen when we want to build or just negotiate a VPN tunnel using IPsec. And once again, we are still with Ike v1 as the implementation of ISACAMP. So IPsec VPNs are negotiated in two different phases. Phase 1 negotiation, also known as the establishment of management connection, can be performed in one of two modes, aggressive mode or main mode. Now, at a high level, I can tell you that the goal of this phase 1 negotiation is going to be to come up with a secure tunnel, which will be then used to protect second negotiation, phase 2, which is always performed using the so-called quick mode exchange. Now, both negotiations take place over UDP port 500 by default. It is possible to change this port number when the devices understand so-called net traversal feature, which is when there is going to be which is the ability to detect network address translation that is taking place between our VPN peers. Because normally what happens is when you do that translation, when you change addresses on IPsec packets, like when you do the network address translation between the VPN peers, this could break the whole communication. So it is going to be important to account for that and possibly fix this translation when it is supposed to be performed. And that's the purpose of net traversal. If net traversal was used, the devices would change the default port number to UDP 4500. But by default, if there is no translation between the VPN peers, it is always going to be UDP 500. Now, as I mentioned, the result of the successful phase 1 negotiation is going to be a so-called Ike SA, or just Ike Security Association, where a security association is a concept that describes a single database that stores parameters negotiated by our VPN peers. So our VPN devices, when they do this phase 1 or phase 2 negotiation, the things that they will negotiate, they will put them into that so-called SA, or the security association. And this security association database will be then used to decrypt or encrypt our data packets. Or in case of Ike phase 1 SA for control plane functions. So once we have this Ike SA tunnel built, we will then perform the second negotiation within that Ike SA, and as a result, we're going to come up with two so-called IPsec SAs, or just tunnels that we will then use to protect the data packets. So if I were to visualize that, there is always going to be a device that initiates the tunnel, which is known as the initiator, and we will have a device that replies, known as a responder. So now, depending on what mode we actually use for phase 1, we're going to see 3 or 6 messages here. But at some point, well, the first packet is always generated by the initiator. And at some point, the devices, assuming the negotiation is successful, they will come up with this secure Ike SA, which is obviously the protected encrypted tunnel. So this is sometimes also known as phase 1 SA. Phase 1 SA or ISACAMP SA or Ike SA, it's a different name for the same thing. And this tunnel, as I said, is used to protect our second negotiation, phase 2. So this is quick mode exchange, how it is performed. Okay, and the result of this second negotiation is going to be two other essays, or just other tunnels, one for inbound and one for outbound data. So these two are known as phase 2 tunnels, phase 2 essays, and once again they are used to protect our data packets. Okay, once those security associations are built versus negotiated between the devices, they will be always associated with a certain lifetime value, and before the lifetime of ASA expires, the devices will essentially renegotiate the tunnels. We will talk about renegotiation at the end of this session, but the goal is just to change the keys so we don't use the same set of keys all the time. But this is just to improve the overall security of our tunnels. Okay, so if we now take a look at the details of phase 1 negotiation, it can be subdivided into 3 stages or just exchanges. The devices will first and foremost exchange the policy. Then we will perform Diffie-Hellman exchange, and finally do the authentication. And as I mentioned, there are actually 2 ways how this phase 1 negotiation can be performed. We have 2 methods for it. We can either use what is known as a main mode exchange, which uses 6 messages to perform the negotiation. And this is generally speaking a more secure solution than the second method, which is known as aggressive mode, where aggressive mode only needs 3 packets, so it is generally less CPU intensive, which is not a big deal as of the current platforms. It was an issue like 10-15 years ago, but not necessarily now. It is a little bit faster, it takes less resources, but it's generally less secure because of the fact that identities of our devices, known as IC identities, so this is basically an identifier of a VPN device, they go unprotected, unencrypted, they are sent in clear along with authentication hashes. And I'm talking about the situation when you do this aggressive mode exchange when pre-shared key is configured for authentication. Because we don't have a problem like that when we use digital certificates for authentication. This is gonna be a fully secured negotiation when we go for certificates and the aggressive mode. It's not a big deal here. The problem is when you use keys for authentication and you are using the aggressive mode exchange. It is still a useful solution for remote access tunnels. So when you build a remote access VPN and you're using keys for authentication, because the problem with remote access VPNs in general is that our server device, or just the device that is kind of like aggregating all those remote connections to provide access to the internal network, must be able to select an appropriate key for each of the connecting clients. And main mode could not be used for that type of setup, because in main mode, the only way to select the pre-shared key for the connecting peer is to use the peer's IP address. So remote access VPNs, this is not going to be an option here because we don't really know what will be the addresses of connecting clients. Those clients can be connecting from different locations. They can be using DHCP assigned addresses. Those addresses will change from time to time. We don't really know those addresses ahead of time. And here is where aggressive mode comes into play. In the aggressive mode exchange, identifiers of our devices are sent immediately in the first packet. So just to show you the concept, let's just take a look at these 2 exchanges from a high-level perspective. So once again, we have the device that initiates and replies. Let's maybe first thing take a look at the main mode exchange. So as I said, there are going to be 6 messages here. Message 2 sent by the initiator to the responder. These 2 messages are used to exchange our policy. So the initiator is sending a proposal, a set of policies, and then the responder is choosing the policy that it supports based on its configuration. So I'm going to say selected policy is being returned. Then in message 3, this is how we start the Diffie-Hellman exchange. So message 4 finishes the Diffie-Hellman, and this is the exact moment when we establish a secure IKSA. Because Diffie-Hellman exchange is used to negotiate shared keys for symmetric encryption and integrity over a insecure medium. So messages 5 and 6, this is when we do authentication. And in main mode, this is when we exchange our identifiers. So 6 messages total, and the authentication stage exchange is fully secured with our IKSA, because we already have the keys from the Diffie-Hellman exchange. We can do the encryption and decryption. Versus if this was aggressive mode, we will see just 3 messages. So I am initiating the tunnel, I am acting as a client. I'm sending message 1, which is my policy, which is my Diffie-Hellman information, which is my identifier. So my responder, which is going to be, in this case, a server or just VPN gateway, replies back with a similar information. So selected policy, Diffie-Hellman, its own ID, and authentication hash. And then message 3 is going to be authentication hash of the initiator. So the problem here is that the authentication hashes and the identities, this stuff is generally sent in clear. And there is a potential that someone could be trying to brute force authentication hash by guessing the key, and this way break our pre-shared key that we use for authentication. So less secure method, but since identifiers, I'm talking about this identifier here, the identifier of the initiator is sent in the first packet, the responder can use this information to find the right key, and this way authenticate the client. So our server can be configured, for example, with this information. VPN peer number 1 should be using key of Cisco, versus VPN peer 2 should be using Cisco 2. And again, something like this, you couldn't do that when using main mode for negotiation. In our next video, we're going to talk about AAA. AAA, or Authentication, Authorization, and Accounting, is a security framework for enabling 3 different security functions. Authentication is a process of claiming an identity and then proving this identity. Like, for example, when you specify a username and then you will provide a password to authenticate. So the reason why we authenticate is obviously to access a given system or certain services. We will have to identify ourselves and then prove this identity. And there are generally 3 major categories of how we can prove that identity. We have something that we know, which could be a password or a PIN code. We have something that we physically possess or something that belongs to us, like a smart card, maybe a token. And finally, we have something that we are, like when you enable biometric-based authentication. So this is actually possible to combine these authentication methods. And when you combine at least 2 of these groups of authentication methods, it is what makes so-called multi-factor or just multi-element authentication. So ideally, the most secure solutions are going to include 3 of these elements. So you will provide a username to a system, then you will have to provide a password. Finally, use your smart card to provide an additional authentication code, and in addition to that, also include biometric data, like maybe they will scan your retinas, or you will place your hand on the scanner, or maybe just a finger. And in that case, we would be talking about a free factor authentication solution, the most secure authentication method. Okay, assuming that authentication was successful, so we got authenticated to a system or to the network, we can now optionally enable what is known as authorization. Authorization is a process of determining a level of access that we will get on a given system or network or just device once we got successfully authenticated. So authorization can be only performed after a successful authentication took place. You cannot authorize someone or something before authentication took place because you don't know what is the identity of the device or that person. So this is how we will enforce our policy. Most cases it's going to be stuff like limiting access to the network. Maybe you will download an access list that controls how far can you go in a given environment. And then in case of device administration, it will be something that limits access to the commands or just things that we can do on a given system. And finally, counting, the third element of the AAA framework is how we can track or just log our activities. So we know exactly when something happened or just what happened on a given system or in the network and when it happened. You want to store this information for situations like when there is going to be a problem. In our network, we have to troubleshoot something and we want to go back and see what happened, who did the changes, what kind of changes, and so on. Okay, we have two major ways how we can deploy our AAA solution. We can deploy this technology directly on network devices, like for example, switches, firewalls, maybe routers. We can configure AAA directly on those devices, and this is where our configuration can end. But this is not a scalable, not a recommended solution. In most cases, it's going to be a bad design if you want to deploy AAA locally on those network access devices, NADs, because it's not scalable, not a scalable option. Think about when you want to change configuration, change something in this AAA configuration on, let's say, 100 of different devices. You would have to reconfigure every single device one by one. And obviously, when you add a new device to the network, you also have to configure it with certain AAA settings. So you probably want to keep this stuff unified across all devices. So you would be using some sort of templates to do this. But again, if you are planning to make a configuration change, adjust this policy, you have to do it everywhere on every single client network access device. So not scalable, and also certain AAA functionality, especially accounting, is not possible to be implemented locally on those devices. So it is a better option to use a centralized AAA, which is where we are gonna configure our devices, our network devices, as AAA clients. So this is what we call network access devices. This is basically another name for AAA client. And then we will also configure our AAA server. And the way that we will communicate our clients with our servers is going to be by using Radius or TACACS Plus. So we have two main security protocols that are used, could be potentially used in our AAA deployment. So once again, just to summarize what I just said about the client and the server, in a centralized deployment, we are obviously going to configure our clients, but it's going to be pretty much a lightweight configuration. We will just tell those devices how they can reach our server and also what services that we want to enable on those clients. So we will have our switches, our routers, maybe firewalls, and those devices will be acting as NADs, or just again the clients. And then they will be connecting to the single AAA server using either Radius or TACACS, maybe both protocols depending on how we have configured those devices. So it's going to be either Radius or TACACS, maybe both. So the clients are going to be they will be sending some sort of requests to our server, and then the server is going to reply with our AAA information. So like with a regular client-server architecture, we've got requests from the clients and then the replies back from the server. Okay, so let's now talk about the differences between Radius and TACACS Plus, because there are a few. Well, first and foremost, what is the reason why the first or the second of these two protocols were actually created, they were designed? So the motivation that stands behind Radius was generally different from the reason why TACACS Plus was created. The Radius stands for Remote Access Dial-in User Service, and this protocol was originally designed to extend layer 2 authentication boundary across layer 3 networks, so that this layer 2 authentication, like from a client to NAS, like when you are doing PPP authentication, for example, could be extended across multiple layer 3 networks to a single central AAA server. Now, TACACS Plus, on the other hand, which stands for Terminal Access Controller Access Control System Plus. I mean, the TACACS Plus is technically the Cisco's version of TACACS. The original TACACS, that didn't have the plus sign at the end. It was simply Terminal Access Controller Access Control System. This protocol was created to provide access to the Unix terminals and mainframes. Now, the current version of TACACS, TACACS Plus, this is Cisco proprietary solution, and it is primarily used for device administration. So in case of Radius, we are still talking about network access. It could be still that extension of layer 2 authentication to layer 3, like for example when you do ADU to the length authentication, but it could be also regular layer 3 based authentication solution. The goal of Radius is generally to control access to the network, versus TACACS Plus is going to be a better choice to provide control access to the devices. Like for example, to manage our router switches or firewalls, just for device administration. Okay, there is also a difference in the transport between these two protocols. The Radius uses UDP, and we have two sets of ports here. The old set of ports is 1645 for authentication and authorization. 1646 is for accounting. We could also switch and use the newer ports, which is 1812 for authentication and authorization, and 1813 for accounting. Now, in case of TACACS Plus, we have just one port. This is TCP49. It is used for all three functions: authentication, authorization, and accounting. Okay, another difference we have in how secure a given protocol is in terms of encryption. So with Radius, this one is only going to protect our password, but the username and authorization data that could potentially come in a reply, they are stored, they are sending clear, versus TACACS Plus is more secure, but because it encrypts the entire payload of the packet. So only the header goes in clear, which means that our username, our password, and authorization data, they are all encrypted. Okay, there is also a difference in the protocol design in terms of how the protocol operates. So Radius always combines authentication with authorization, versus TACACS Plus separates all three AAA functions. So what does that mean? It means that when you do authentication with Radius, when you get a reply, you also expect the server to send you some authorization data. It could be a simple yes for authorization was successful. It could be something more sophisticated, like for example an access list or a VLAN number. Now in case of TACACS Plus, when you do authentication, you don't necessarily have to do authorization in the same exchange. You can authenticate to a system initially, like when you start a session, and then when you're in the middle of the session, you already did something, and then you will do something else which was configured for authorization, which means that authorization is going to happen later down the road, not initially right after that first authentication. And you cannot do something like that with Radius. Radius always combines authentication and authorization, which means that authorization with Radius can only happen once along with authentication. At least when we talk about the original specification of Radius without any additions. Okay, another difference is that Radius is an open standard. It was created by IETF versus TACACS Plus is Cisco proprietary solution. And one more is that Radius supports extensible authentication protocol. This is why you can actually use it for 802.1x authentication versus TACACS Plus does not support EAP. Again, TACACS Plus is generally used for device administration. Right, another thing we should know about the protocols, Radius and TACACS Plus, is how they exchange the information. I am talking about the client to server or just server to client information exchange. So both protocols, they use the so-called attributes for this purpose, where an attribute is just a container for a certain piece of information. And attributes can be of different type, which defines what kind of information we are going to carry within the attribute, and the actual information is carried as a value. So this is why we typically refer to those attributes and values as AV pairs. And again, both protocols, they use the same concept of attribute and value. It's just a different description of different numbers or just names of those attributes, what they use. Like for example, in case of Radius, those attributes are essentially numbered. This is how we identify the attributes. In case of TACACS Plus, both the attribute and the value are generally going to be strings. A few words more about Radius. The original IETF specification predefined, it allows for up to 255 attributes, and many of these attributes are actually predefined by IETF. And in most cases, they will be sufficient. I mean, most vendors who make the network equipment, they will be extensively using those attributes. But there could be situations that a given vendor or just vendors, they require the exchange to carry their proprietary information, which is not suitable for public use. And because of that, a so-called vendor-specific attribute, vendor-specific attribute, or just VSA, was created by IETF. It is technically attribute number 26. This attribute can be used to encapsulate additional information, which is going to be vendor-specific. Like when, for example, Cisco wants to carry some proprietary information over Radius. So this attribute consists of three fields. We've got the vendor type, we've got ID, and then the length. And the most commonly used VSA, at least the one from Cisco, is known as a Cisco AV pair. And this attribute was created originally to extend that basic Radius functionality with some TACACS Plus capabilities. Like for example, so you could use Radius to provide partial control of device administration. So you could use Radius for device administration and support at least some of those functions that TACACS Plus offer. So Cisco AV pair uses this, a protocol colon attribute equal to value format. Like for example, shell colon priv level equals 15. It would mean that you want to place a user who is connecting to a device into privilege level 15 after a successful authentication, after a successful authorization. So the user would have to first thing authenticate, and then you would place that user into level 15, and you would be using Radius for this and not TACACS Plus. Okay, we have two major AAA server implementations from Cisco. One is known as Access Control Server, or just ACS, and the other one is known as Identity Services Engine. The ACS is more of like a less advanced solution that we still can use to implement full-blown AAA services, either with Radius or TACACS Plus. So you could use ACS for device administration and for network access, but it doesn't offer any type of advanced functionality, like for example, profiling, which is offered by Identity Services Engine. Well, let's now focus on ACS. So again, the full-blown AAA functionality, this is what we can do with ACS. We can do authentication, authorization, and accounting for network access with Radius. We can do device administration with TACACS Plus. This device can be also integrated with an external authentication database, like for example Active Directory, and it is available as a one RAG unit appliance or as a virtual machine on a VMware server. Okay, the old versions of ACS, they were using an identity-based policy model, which means that you were configuring your policy, like authorization policy, under individual user accounts or maybe under a group of users, under the group accounts. So for example, if you wanted to build an access control solution for device administration, where you designated a certain group of people with full read-write access to your router switches, you would placing this policy, the actual authorization data, under the group definition. If you wanted to make exceptions, you're modifying individual user accounts and adding exceptions there. Now, the newest implementations of ACS, which are versions 5 point something and higher, they follow a rule-based policy model, which means that our policy information, the authorization data, is decoupled from the user and group definitions. Instead, you're going to be defining this information centrally. You're going to have a policy for authentication, for authorization, and both policies are going to be using that if condition then result approach. So we have a lot of different flexible conditions we can use in those policies, and then specify that if a given condition is met, what do we want to do with the session. Obviously, authorization data, the authorization policy, this is how we will enforce what we want to do for a given session or for a given user. In case of Identity Services Engine, the newest code of ICE, it also supports TACACS Plus, so you could still use ICE for both network access and device administration. This is a powerful next generation identity management system that can be deployed to fully control access to the network and again also to the devices with the current codes. It is an advanced combination of ACS, so pretty much anything you can do on ACS you can also do on ICE, plus it offers you some advanced functions like for example network addition control and some other features. ICE is also going to act as a main component of every single TrustSec deployment, where Cisco TrustSec is the newest model for deploying secure network environments. You can integrate this solution with an external database for authentication, like Active Directory or maybe RSA one-time password solution. So somewhat similar to what ACS can do. And you can also deploy ICE as either a hardware or virtual appliance. And some of the advanced features that this device offers, we have profiling, which is the ability to detect, localize, and define connecting endpoints. So we can tell if the device that is connecting to our network is, for example, an IP phone, or maybe a printer, or maybe a corporate laptop. We can enable it to perform posture assessment, which is how we determine the overall health of the connecting endpoint. For example, you could take a look if the current level of operating system patches, the registry settings, or just the antivirus software version updates are compliant with your current policy, and make a decision based on that information as what to do with the endpoint. And we can finally configure ICE to deploy what is known as central web authentication, which is a centralized and a scalable solution for providing guest access or just temporary access to our network. In our next session, we're going to take a look at the basics or just fundamentals of intrusion detection and prevention systems. And we will take a look at the different types of devices that we can deploy in our network to detect or prevent attacks. And we will talk about how to deliver the traffic to our devices for inspection. And we will also quickly look at the detection methods and actions that might be taken by our sensors. And finally, we will also briefly discuss a terminology related to IDS IPS systems. Okay, so first and foremost, what is going to be a difference between the detection and prevention systems? Because an intrusion sensor can be defined as one of these two. It can either just detect the attacks, which is known as an IDS system. So an IDS is a sensor that is capable of detecting the attacks, but generally speaking is not able to stop those attacks once they are detected. Now, the way that we will be configuring our sensor as IDS, as we'll see in just a second, is going to be by copying a traffic from the network to an interface of our IDS so that it can analyze those packets. And now this in turn means that our device is going to be working on a copy of the real traffic, not on the real packets. And because of that, even when it detects the attack, it will not be able to stop it. There are actually two small exceptions to this rule. One is going to be for TCP-based connections. Our device could potentially send a TCP preset packet and this way protect the victim from receiving the offending packets. And the other solution is going to be to rely on a different device in our network, like for example an iOS router or maybe ASA firewall, which we will then ask to stop the attack, like for example by applying an access list. Now, in case of a sensor configured as a prevention system and known as IPS, the device is not only going to be able to detect the attacks, but will be also able to stop them. So in this particular case, our sensor is going to be placed in line with the real packet flows. It is going to be able to act on real packets generated by our applications, clients, so generally on the traffic that is traversing through the sensor. Now, most of the sensors available in the market today, they can be configured in one of these two modes. It is actually even possible to deploy both modes on a single physical or virtual device. So it's going to be pretty much our configuration, which is going to eventually affect how our sensor is going to behave. Is it going to act as a detection or a prevention system? Now, if you want to deploy an IDS, you will have to configure your device, actually, technically its interfaces, in a so-called promiscuous or a passive mode. Now, this in turn means that the device is going to be listening for packets from the network, so we will have to somehow deliver those packets to our device for inspection. And this can be accomplished by using SPAN, remote SPAN technology, or maybe by using a physical connector, which is going to mirror the traffic flow to our IDS and known as a vampire tap. Now, in case of SPAN or remote SPAN, we're going to be configuring our switches to copy real packets from one place and then send them to the IDS for inspection. So just to quickly show you the concept, let's say that we will configure what is known as a SPAN session, which means that we're going to be dealing with a single switch, and this switch is going to be connected to our IDS. Let's say that this is going to be on port F07. And this is also where our clients, or just the traffic that we want to copy, is going to be connected to. So like when we have two devices, host 1 and host 2, both are connected to the same VLAN, just different interfaces of our switch, like F03 and let's say F04. So we might configure this switch to copy the traffic that is received or sent via those interfaces and send it to the IDS for inspection. Now, if we had multiple switches, like for example, another switch over here, let's say that this is going to be Cat 2, this one was Cat 1, and we have one more, let's say Cat 3. You could still configure a similar solution, but whenever multiple switches are involved, we are going to be talking about remote SPAN. So in this case, we would have our IDS connected to a different switch from where the traffic we want to copy is flowing. Like for example, our IDS would be connected to switch 3, but we would want to copy the traffic that is going between switches 1 and 2. Maybe we have a different device here, like host 3, and we want to look at communication between host 1 and host 3. So this communication will be going between the switches. So with remote span, you would be able to configure all switches here to send the copy of this communication to a special VLAN known as remote span VLAN. And then on our destination switch, which is where our IDS is connected, we would copy the packets or just send the packets from that VLAN down to the IDS. Okay, the main benefit of promiscuous or just passive mode is that our IDS cannot become a bottleneck in the network. Because once again, the real packets will be unaffected by our sensor. They're kind of like bypassing our device because what we send to the device for inspection is just a copy of real communication. Now, in case of the inline deployments, which once again means that our device is going to now act as an IPS solution, we're going to be putting our sensor in line with the real data packets. And this can be generally accomplished at layer 2, like when you place an IPS between the switches, or you might also configure your device to route packets between different subnets, which is going to be possible in case of firepower devices. Just a quick example of how your deployment could look like at layer 2 when you deploy inline device. You could configure your switch to trunk to the sensor. Like select one of its interfaces connected to the IPS, configure a switch port as a trunk, so this interface, and then we could put our clients, or just the devices that belong to the segment that we want to monitor, in different layer 2 networks. Like we could put our host 1 in VLAN 10, and we could put a different host from this subnet in VLAN 20. So those devices will be completely unaware of this layer 2 disconnection, because once again, we're going to put them in a single layer 3 subnet. They will be in the same subnet. Like for example, host 1 is going to be using some subnet .10, host 2 is going to be using .20 in the fork octet from this subnet. So those devices will think that they are directly connected. And then when host 1, for example, wants to talk to the second host, so it sends a packet with a destination of host 2. It is going to first thing obviously have to ARP for the layer 2 address of host 2. But the packet is going to be sent to the physical address of this second host. And the packet is going to be received by the switch in VLAN 10, which means that the switch is going to send it down the trunk with a tag number of 10. And now when IPS gets the frame, it is going to first thing inspect it. And if the sensor is okay with the packet, it is going to send it back the same interface, but with a different VLAN number, with a number of 20, which is going to correspond to the VLAN of the second host. And obviously a similar process is going to take place for the opposite direction. So when host 2 replies back to 1, the tag of 20 is going to be replaced with a number of 10 by our IPS after inspecting the packet. We obviously, in this case, we assume that the packet is allowed for our sensor. Obviously, the inline mode has a serious advantage over our passive or promiscuous deployment, which is going to be that capability of preventing, not only detecting, but also stopping the attacks. But a problem here is that, well, so the device can actually stop the attack, the traffic must go through the sensor in the first place, which means that our device could potentially affect the communication of the traffic flows that are going through it in terms of the bandwidth usage and the delay, maybe latency. So our device could potentially become a bottleneck, like if you didn't plan accordingly for the interfaces for the actual platform. There's also a concept of so-called fail close or fail open mode for inline configuration, which is related to the traffic processing when our inspection engine fails. So for example, our IPS was configured in the inline mode, and it is forwarding and inspecting packets as what it should normally do. Now, for some reasons, our device, our engine, inspection engine fails. And if we were to configure our device in the fail open mode, it would mean that the sensor would still forward the packets, all packets, good and bad, in both directions. Now, if you were to configure it in the fail close mode, it would mean that our device would be blocking all packets, good and bad. So fail open versus fail close, once again, it refers to a situation when our inspection engine fails, and what do we want to do with the traffic? Do we want to allow it or block? Our intrusion sensors can be generally divided into network-based or host-based systems, or in case of network-based solutions, we are talking about NIPS. In case of host-based or just endpoint-based systems, we talk about Edge IPS. And there are going to be some differences between these two types of sensors, so we will now take a look at them. First and foremost, our NIPS can be deployed as a physical appliance, like for example, Firepower 7 or 8000 device. It can be deployed as a VMware image, or it can be configured as a module installed on our iOS or maybe ASA, like ASA Firepower inspection module. Now, in case of host-based prevention or just Edge IPS systems, the way that this is implemented is by installing a software on our endpoints. And in the old days, what we used to do is that we were installing a full-blown IPS IDS software known as an agent on every single endpoint in the network. And those agents, they were taking a lot of CPU cycles, a lot of memory to do the actual inspection. So a better solution, which is commonly used right now, is to use a cloud-based deployment for Edge IPS, which means that what we install on the endpoints is not a full-blown software, intrusion detection prevention software, but a lightweight software that is used to provide connectivity for the endpoint so it can connect to our prevention engine in the cloud. So in this particular case, we kind of like offload the processing from the endpoint to the cloud, and those connectors are only used to provide connectivity for the endpoint so it can communicate with our engine in the cloud. And there's going to be some advantages of an Edge IPS. There are going to be some things that our NIPS will not be able to perform. So first and foremost, in case of Edge IPS sensors, these are capable of analyzing encrypted traffic flows. So this is something that most of the current sensors cannot do when you send an encrypted connection for a network-based IPS, versus on a host, since decryption is going to happen before analysis or just inspection. It means that when analysis engine kicks in, it is going to act on the clear text or just decrypted communication. So this is one benefit over NIPS. And then the second one is that Edge IPS is going to be able to detect attacks that NIPS cannot, which are going to be attacks that don't generate or just require any type of network activity. Like for example, when someone gets physical access to the endpoint and obtains unauthorized access to the device and modifies or removes certain files. So this obviously couldn't be detected by our NIPS because there is no traffic flowing in the network that is used to modify, provide a session to the endpoint to delete those files, versus Edge IPS is going to be able to detect such as activities. Okay, so lots of good things about Edge IPS over NIPS, but those systems also have a major drawback comparing to network-based systems, which is generally speaking a burden related to administration. So first and foremost, not every single operating system is going to support that host-based system that you might want to use. And even if they do, you will still have to install the actual software on all endpoints. And then you will have to somehow manage this software. Like when you want to access the endpoint or just the software remotely, it's going to be a huge problem, a challenging task how you would actually accomplish that. And now a couple words about the different detection methods that our sensors will be using in their operations. So there is going to be several different solutions that our IDS IPS system will use to detect an attack. And the most common is going to be known as a signature-based detection, where a signature can be simply defined as a file which contains the rules and conditions that describe an offending packet or packets. So signature-based system, most of the current IPSs, IDSs will rely on the signatures, at least up to some extent. And those signatures will have to be downloaded from the vendor, because again, the attack detection based on the signatures relies on individual files which contain a description of an attack. So obviously, so that the attack can be detected, we will have to download a given signature that describes that attack. So generally speaking, you will want to keep the signature base up to date all the time. And the problem related to that is that if you, for some reason, don't manage to download the latest signatures, your device might not be able to detect one of the newest attacks which was just launched. So generally speaking, this method is also not going to be able to detect so-called zero-day threats, which are attacks that has not yet been published. So another thing that we might want to configure on our sensors is known as anomaly detection. And here, instead of relying on signatures, we're going to add some sort of artificial intelligence to the analysis process. And this is going to be done by, first and foremost, configuring our device to learn the normal activities in our network, like to see what are the different regular flows in our network, and kind of like save this information into a profile, make a baseline profile of what normal traffic is in our environment, and then keep using this profile, comparing it to the current activities, looking for anomalies. Another option is going to be to configure a policy statically through a set of rules, where those rules will describe what a normal traffic is. And whenever we see communication, flows that kind of like don't match those rules, we're going to fire up a signature. Well, obviously, the problem with this method is that there is going to be huge administrative overhead related to the configuration, and the actual configuration might be quite challenging to make it work for our environment. And then the last method is known as a reputation-based detection, which is when we will rely on an external database, which is going to contain information about the attackers in form of their IP addresses, maybe domain names, URLs. And each of those elements, they will be associated with a certain reputation value. So if a given IP address, URL, or maybe domain name has a really bad reputation, we will be able to block the packets coming from this given address or just a domain. In our next video, I'd like to talk about some of the layer 2 attacks. So in the next two sessions, we're going to take a look at a couple of different attacks commonly seen at layer 2. And in this session, we're going to focus on MAC spoofing and MAC flooding attacks. We will then talk about VLAN hopping and certain attacks on STP. And then in our next session, we will also cover attacks on DHCP, ARP spoofing, and spoofing of IP addresses. So let's go ahead and start our discussion with MAC spoofing, which is when someone sends a frame or just a packet with someone else's MAC address in the source. Why you could actually want to do something like this? Well, it's all about how the switches populate their CAN tables. So we know that switches, when they do the forwarding of the frames, they will extensively rely on this CAN table, which is like a layer 2 equivalent of a layer 3 routing table. And the switches will be looking into that table to find the outgoing interface for a frame. Now, the way that this table is populated is by adding entries based on the sources seen in the frames that are going for our switch. So when a switch gets a frame, it goes takes a look at the source address in the frame. I'm obviously talking about the layer 2 source address. And it is now adding this address to the CAM table, assuming that there was no entry associated with this address in the CAM. So this is how the switch populates the CAM table. This process is obviously not secure, and it is dynamic in nature. And it is pretty easy to override the information which is already stored in the CAM. It's just a matter of sending a packet with a certain source, and the switch is gonna include this information, rewriting the CAM table if it already had an entry for that MAC address on a different interface. So this is exactly how this attack is going to be performed. The switch is going to update its CAM table entry for this changed address, and it's going to point to a different interface. So just to show you what is going to happen specifically here, let's say that we have a single switch which is connected to two devices. We have PC2 and we have PC1. Okay, those devices, we will say that they will be using specific MAC addresses. Like PC1 is going to be using MAC address M1, and PC2 is going to use MAC address M2. So obviously, in reality, those addresses are 48-bit strings. But for simplicity, just to make this whole explanation easier to understand, we're going to keep those addresses shorter so you don't have to think about what address is associated with what device. Okay, so now what is going to happen is that when PC1 wants to talk to PC2, assuming that it has a correct layer 3 to layer 2 mapping in its ARP cache, because we assume that we are using Ethernet network here, it is going to send a frame with a destination of M2 and with a source of its own address, which is going to be M1. So this is going to cause the switch to populate its CAM table. We assume that we start with a brand new CAM. There was no packets sent by those devices previously. The switch is going to add an entry for PC1. It is going to associate MAC address 1 with, let's say that this is going to be FO1 interface where PC1 is connected to. Okay, so this way the switch is going to know that when it gets a frame with a destination of M1, like when PC2 sends a packet, it is going to do this CAM table lookup, find the outgoing interface, and it's going to send the frame out of the correct port. But once again, since I mentioned, like what I mentioned, this CAM update procedure is completely dynamic and insecure in nature. If someone is able to put another device into that VLAN, let's say to FO3 interface, so this is going to be the attacker. This attacker could simply start sending packets or just frames with spoofed sources, which in our case, let's say it is going to send a packet with a source of M1. It can do this, something like that, but it's not a big deal to make it work. You just have to have some sort of a tool that allows you to craft frames with specific addresses inside of it. So when the switch is going to get the packet, it is going to take a look at the source of the frame, and it is going to realize that this MAC address should be now associated with a different interface. So it is going to erase this original entry of FO1, and it is going to associate it with FO3, which is the attacker's port. So that in turn means that when our PC2 sends a different packet with the same destination of M1, this packet is going to be switched out of FO3 interface down to the attacker's station. So this way the attacker can actually get the packets coming from other devices, can capture them, and potentially sniff or just read the content if communication is unencrypted. Okay, another type of attack that we have here is known as MAC or scam flooding. With this attack method, someone is going to be generating a large number of frames with completely random spoofed source MAC addresses. So we are still sending frames with different addresses that don't belong to us. But in this particular case, we will be probably using non-existing addresses. They will be randomly generated because the goal is going to be to fill up the CAM for a given VLAN. So every single VLAN on a switch has a finite number of entries for its CAM table, like for example 8,000 or maybe 9,000 entries depending on the platform and on your SDM template configuration, but this number is obviously limited. So the problem is that when the CAM table gets fully populated with those different spoofed MAC addresses, we leave no place for legitimate addresses, which means that when we then get traffic from the devices in our network, like from legitimate hosts, which want to communicate with other legitimate devices, assuming that the addresses of those valid stations are not already in the CAM, like for example because they were inactive, they weren't sending any data, we will not be able to forward that frame out of a single interface like what the switch should normally do, because the switch will not have an entry for this valid destination. And the end result of this is going to be that the switch is going to flood that frame out of every single interface except the one where the frame came in. So it is going to kind of like turn the switch, it is going to force the switch to behave like a network hub. Okay, so if we take a look at this, let's say that our switch has two entries in its CAM table. And let's say that this is going to be for MAC address 1, MAC address 2. This is associated with the FO1 interface. This is associated with FO2. And then let's say that someone starts this flooding attack, which is going to fill out the CAM table with random addresses. Like, MAC 7, MAC 10, and let's say MX. MX is going to be the last address. So in a situation like that, when someone is sending a frame with a destination of M1, we still have an entry for M1 in the CAM, so we will send the packet out of FO1 interface. And the same situation is going to apply for M2, just a different interface. But how about if we get a frame with an address of a legitimate device which is not in the CAM table, like M123? Okay, so we don't have an entry here in this CAM, which means that the switch is going to flood it out of every single interface except where the frame was received on. And even more importantly, for those legitimate entries that we already have, like M1 and M2, assuming that those devices stop sending data packets, those entries will at some point time out. And if attacker is still flooding our switch with randomly generated frames, we will eventually add something random here. And this way, at some point, it is possible that no single valid MAC address of our clients will be included in the CAM table, which means that all packets destined to legitimate devices, they will be flooded out every single interface, again, except the one where the frame was received on. So the end result of this attack is that someone is able to see the packets coming from all other devices in a given VLAN. Okay, so how do we mitigate that type of attacks? A mitigation is going to be to enable so-called port security feature, and this feature can be used to prevent against these two attacks, MAC spoofing and MAC or the CAM table flooding. So what is port security? A port security is a layer 2 security feature that is used to enable two individual mechanisms on our switch ports. One is going to be to identify the addresses that we want to allow on a given switch port. So this is going to prevent MAC spoofing attacks. We will be able to tell exactly what addresses are allowed to communicate for a given port versus everything else is going to be blocked. And then the second mechanism of this port security is used to prevent against the flooding attacks. We will be also able to specify a limit for legitimate addresses that we want to keep in the CAM, or just specifically in the port security table, but this way also in the CAM. But let's first focus on this first option here, which is to identify the actual addresses, because there are actually going to be 3 different methods as how we can do that. So the default method of learning addresses is going to be to go to the CAM of the switch, take the addresses from the CAM for a given interface, and put them into the port security table, which is how we will enforce our policy. The indifferent method is going to be to still take a look at the CAM, take addresses from that place, but in addition to putting them into the port security table, we will also put them into the running configuration. And finally, method 3 is going to be to learn those addresses manually, which is when you will essentially configure them on the switch. And as I said, the second mechanism that is offered by port security is going to be just to limit the number of addresses that we want to learn or just allow for the port. And the default limit, which is set when you enable the feature, is going to be just 1 address, like when you connect a single device. Now, the question is, what is going to happen when either a limit of the addresses was exceeded on the interface, or when we see traffic coming from addresses that are not allowed, not included in our allowed list for a given port. So this is when a so-called violation is going to be triggered by port security, which is when our switch will, by default, shut down the interface. It is going to put it into the error disabled state, which is effectively shut down. Another option we can enable is going to be to say shut down, but just the offending VLAN, which is going to be useful, for example, when you enable this feature on trunk interfaces. We could also say restrict, which is to drop frames coming from those unknown or just unallowed addresses, generating a syslog message, SNMP trap, and increasing a violation counter. And finally, when you say protect, it means that you still want to drop packets coming from those unknown addresses, but you don't want to generate a syslog or a trap.